understand as I go through my talk, which is using low field NMR relaxation measurements in the formulation of suspensions from fundamentals to end use. Yesterday, of course, you were on the seminar with Terry Cosgrove, who talked to you about a new low field device, the Mageleka Magnometer. My talk today is focused on measurements and applications using such a device. So, why from fundamentals to end use? This slide is one I use when I talk about formulating products, and it shows a schematic of the various stages from raw materials through to a final commercial product. Now, I'm not going to go into a lot of details, but clearly the preparation of particulate suspensions starts with raw materials. Too often, little thought or attention is paid to this initial step. Differences between nominally identical materials because of variations in mechanical and chemical processing methods can influence the performance of any subsequent procedures that use them. Now, many particulate materials are made or used as suspensions in liquids, and it is this particle-liquid interface, no matter what the particle, no matter what the liquid, that controls product performance. And product performance is defined as what the suspension is designed to do or be used for. I'm hoping to show you that NMR relaxation measurements are uniquely sensitive to two important features of any particle-liquid interface. The first is the extent of wetted surface in a suspension, and the second is the chemical nature of a particle surface. And as seen in the schematic, this influences the changes in the influence of changes in these two fundamental parameters permeates every subsequent aspect of suspension formulation, manufacturing, and testing. Consistency in stability and structure characteristics of suspension is a prerequisite for obtaining the desired final product quality, the performance of which, of course, is measured by a very sensitive instrument indeed, namely the consumer. So what I hope to do now through a series of small applications is to show how measurements using the magnometer can find use at each stage, literally from fundamentals to end use. So why use NMR relaxation? I'm not going to say anything here, but it's importantly, you can use it just about in any application you can think of. But the main feature of NMR relaxation that makes it very useful is that measurements can be made at virtually any industry relevant solids concentration without the need for dilution or much sample manipulation. If you can get the sample into an NMR tube, you can make a measurement. Let's start at the beginning. The preparation of any suspension or slurry typically begins with a dry powder material. Unfortunately, raw materials are never 100% pure, and this is true even for pharmaceutical grade material. Industrial material can contain as little as 80% of the active components if you bother looking at the typical material safety data and technical sheets that are actually supplied with material. But in all cases, the type and level of impurities depends upon the source of the material and any subsequent processing. So what I'm going to show here, two widely used chemicals, very simple ones, an alumina and lime. Alumina basically is produced from bauxite ore mined in different parts of the world, and the four samples I'm showing here were sourced from Australia, Brazil, West Africa, and Russia. Now you can see the figure on the right here, excuse me. You can see that the measurements of the relaxation number. And a relaxation number basically is essentially the inverse of the relaxation time itself. The reproducibility of these measurements, by the way, is very good, less than 1% itself there. The results displayed there. And you can see there are differences between them, but they group themselves into two groups. These two here are very similar, and these two are very similar here. So alumina from sources 1 and 3 are similar, as are the materials from sources 2 and 4. Now, I'm saying no more about this other than, of course, the differences between them is likely a consequence of real variations in the geometric surface area because of both the size and surface roughness of the slurry material particles, as well as potentially the surface chemistry. The second example, crude mined limestone is converted to slate lime by heating and hydration, but variations in this process can influence the quality of the final product. Now, the materials shown on the left here are from two different sources again, but they were created using different processing conditions, mechanical and chemical. And in this case, I compared them by, as you can see from the concentrations here, I'm putting 11 weight percent in methanol, and this is in 37%. As I said at the beginning, you can use almost any concentration, but the sweet spot for NMR relaxation measurements really is somewhere between 10 and 40%, because typically in those cases the suspensions are flowable slurries. The maximum concentration that I've ever measured personally is a 91% silver paste, and to get that in an open-ended NMR tube provides a little bit of difficulty, but it can be done. But in this case, going back to the lime, now there's a significant difference between the two materials. So it's clear that whatever mechanical and chemical processing methods were used, it had a major impact on the characteristics of the actual lime itself. The NMR relaxation data presented here then shows that for both types of chemicals investigated, nominally so-called identical materials were obviously not the same. In addition then to influence performance of any subsequent procedures that use them, the potential economic impact of variation in these raw materials must also be considered. So one of the problems you have in formulations is if you assume that the beginning material is the same and you end up finding something going on at the end, you do not know whether it started at the beginning or was because of the processing you do. Too few people do what Ronald Reagan used to say was, you trust, but you verify. And the Magnometer is a pretty fast, simple tool for easy comparison of virtually any incoming raw materials. So let's look at the wetting of surfaces itself. The initial step in the preparation of particle dispersions is the incorporation of the dry powder into a liquid. And the liquid can be water, oil, or non-aqueous solvent. Now, it's long been known, and there's a paper by Washburn as far back as 1921, that knowledge of wetting behavior of solvents on surface is important. Basically, from the basic physics and mechanics of the process, but it's also important in a wide range of industrial processes such as surface cleaning, coatings, printings, etc. Now, liquids are affected to different extents by the chemical and morphological nature of the particle surfaces. In other words, the surface chemistry and the roughness. The smaller the contact angle of a liquid for a solid surface, the greater is the wetting. Hence, a knowledge of powder wetting is important to good dispersibility. And how a liquid wets a particle surface is a key criterion and is crucial to understanding dispersibility. But despite the importance of powder wettability, there are actually few reliable measurement techniques to determine wettability of powders. Contact angle measurements are only useful for flat, planar surfaces. Interfacial tension measurements of liquids are generally only applicable to liquids themselves. Although you can use techniques such as heat of immersion, these are expensive, are experimentally complex, and require a long measurement time, characteristics that make it unsuitable for quick routine laboratory analysis. By contrast, NMR relaxation is a fast and easy method to assess wettability for almost any type of solid liquid combination. And by the way, it doesn't have to be powders. You can measure fibers, you can measure sheets, you can, as you roll a sheet up and push it in an NMR tube, you can make a measurement on it. And a paper on this whole subject has just been published in Powder Technology this year itself. So I've just shown here, you can make a measurement on the liquids themselves, and then you can apply any one of those liquids to the wettability of a solid itself. And what I did here was simply take a homologous series of liquids. These were alkanols, and which will obviously have a different contact angle for the surface, and measure the relaxation time. And by doing this, you can determine which liquid, or indeed mixtures of liquids, provides the desired wetting of a powder surface. And in this example, you can see here, although all the liquids will wet the titanium dioxide, what we see is the methanol basically is by far the most efficient. So let's look now at a practical example of this itself. What I'm using here, the powder material used here, was a hydrophobically modified micronized zinc oxide obtained from 3 different manufacturers, one in the USA, one from the EU, and one from Japan. They were claimed to be equivalent products. According to the literature, they had the same nominal particle size and the same silane-based coating. And specifically, if you're looking at it, it was a triethoxy capital silane. Now, for those who are not familiar with silanes, the basic silane is an inorganic compound, silicon hydride. And silanes as a group are compounds with up to 4 substituent ligands on the silicon atom, okay, itself. So you can get a whole variety of these silanes, and they're used as often in a lot of things as what's called coupling agents. But here, the material in question, the zinc oxide itself was used in the formulation of sunscreen products because it's an efficient absorber of UVA and UVB. In its natural state, however, it's hydrophilic, can be wetted by water. But in sunscreen products, it's incorporated in the oil phase. And therefore, you've got to do something to make the zinc oxide. So you can use maybe a dispersant of some sort. But what the manufacturers have done is coated these materials to make it completely non-wetting in water, and so enables it to be incorporated into the oil phase of the sunscreen relatively easily. However, different non-aqueous fluids, oils and solvents will, as in the previous slide, have different wetting ability. Now, in this study here, I showed a comparison of 3 zinc oxides, each dispersed at 8 weight% in 2 different fluids. One was hexane and one was 100 centistoke silicone fluid. This latter material was actually a polydimethyl siloxane, technically called a dimethicone. Now, in the first example on the right, what we see is the powder samples are wetted to almost an identical amount itself. This is likely, of course, because the surface coating is a silane which is very compatible with linear silicone fluids such as dimethicone. However, what happens if the dispersing fluid is an organic fluid and not a silicone, which is an inorganic fluid? In the second example on the left, I just use hexane itself. You could use anything to test this, but as we see here now, when we disperse these zinc oxides in hexane, we get huge differences between this. Excuse me. Sample A here was by far the most efficiently wetted. Sample B, the least. So what this shows is that notwithstanding the manufacturer's claims, the silane coating for each zinc oxide surface cannot be identical, either in composition or concentration itself. So it demonstrates here how well NMR relaxation can be used not only for fast determination of simple powder wettability, but to discriminate materials based via coatings on their surface chemistry. And by the way, this data here is actually the subject, one of the main subjects of the powder technology paper mentioned in the previous slide itself. So using the magnometer, you can develop and create improved suspensions, which in turn, of course, then can result in better and more efficient product performance itself. This also study, I think, highlights the need for quality control of any incoming raw materials and to verify manufacturers' claims regarding product specifications and performance. So, dispersants. An important step in the next processing of dispersing particles is deagglomeration of the aggregated particles, where you simply try to separate the particles from each other. In addition to improving the quality of formulations, the use of dispersing agents can also improve the economics of production because they reduce the need for expensive and labor-intensive mechanical energy milling. Now, there are literally hundreds of dispersants on the market and they all work. So which one is the most effective for a given material and liquid combination? Determining this will result in a suspension with superior performance attributes. Now, the example here shows NMR relaxation data from a series of suspensions, each created with a different dispersant. And what I did is I took a 60-weight suspension of metallic silver flake in a fluid called Texanol. Texanol, by the way, is an alcoholic ester used in paints and inks, and the metallic silver plate is often used to impart decorative properties itself. Now, the shortest relaxation time, reflecting the largest wetted surface area, the best dispersibility, was found in the suspension prepared using the Hypomer KD1, sample E, here. The longest relaxation time, using the Crodefoss M915A, here, there, which performs only marginally better than a suspension prepared without any dispersant at all, type A. So what we've got here is a very efficient one, and one basically here, this Crodefoss, not much better than no dispersant at all. Now, the results can be explained by considering the chemical nature of dispersants examined, but actually that's the subject of another talk. All I want to say is that the Crodefoss M915A turns out to be an alkyl phosphate anionic dispersant, which actually works very well in aqueous dispersions, but it's not going to work very well in non-aqueous ones. Whereas the Hypomer KD1 is a polyester polyamine copolymer that works very well in non-aqueous. So these samples here just show what you should get if you know something about the chemistry of the dispersants themselves. Of course, the others work in intermediate between the two. But what it demonstrates is the utility of the Magnometer of evaluating which dispersant is the most effective for a given material and liquid combination very quickly. You can use the Magnometer to rapidly fingerprint preparations of suspensions using different dispersant types, and so help you in the formulation development. So once you've figured out what's the best dispersant to use, the next step, of course, is to determine the optimum concentration use, which we're going to demonstrate in the next slide. Here, what we're taking is some dispersions of a nanographite. 4 suspensions of the dry powder prepared by small bench scale milling, a constant mechanical energy in the laboratory with increasing addition of a polymeric surfactant dispersant. It was actually a naphthalene polycondensate for anyone that's interested itself. I use nanocarbon because it's everyone talks about it. There's a lot of attention being this because they're being used for a whole wide range of things like supercapacitors, catalyst supports, etc. But the figure here shows the wetted surface area for nanographite suspension starting here with no dispersant, 1%, 5%, 10%. The SP sample is a sample dispersion prepared at 20 weight percent, but using production scale equipment. But again, with no dispersant in, so this and this are the same. This uses bench scale milling, this uses production scale milling. But let's look at these here first. What we see is that the concentration of dispersant was increased. The wetted surface area, okay, also increases, which means you're getting better dispersibility. But once we go above 5% and go to 10%, we're clearly now overdosing because the surface area has gone down. And you're getting now aggregation, and this is probably because of a result of particle aggregation through depletion flocculation because of the nature of that naphthalene polycondensate. But the other observation is this sample here, the bench scale milling and the production scale milling are almost identical. So since you can take samples at virtually any concentration, what I'm saying is you can do measurements in the lab on your bench scale. You can compare it then with real production material and find out what the difference is because of the scale up going from lab to production scale equipment. Now, overdosing with surfactants impacts both the performance of the final product, but it's also expensive. So using NMR relaxation, what you can then do is determine an optimum concentration. Indeed, I'm not sure if I think Terry talked about it, but you can actually do an in situ, an actual adsorption isotherm on the materials itself very quickly, far more quickly than traditional methods itself. Now let's turn our attention to the next stage in a production, sedimentation and stability. Now, sedimentation, of course, is simply the time-dependent deposition of particles due to gravity. The higher the density of material, the faster the rate that the particles settle. The bigger the particles, the faster they settle. And it impacts, of course, the storage of suspensions. Now, there are various techniques available to study sedimentation, such as analytical centrifugation. However, AC is based on the application of Stokes' law, and it's critically then influenced by the hydrodynamics of particle settling and the details of sample prep. AC performs best for spherical particles under laminar flow constant conditions, which requires, it means, dilute suspensions of spherical particles with reasonable narrow particle size distributions. But a large number of industrial materials comprise broad particle size distributions with non-spherical particles. NMR relaxation measurement doesn't suffer from the limitations of this technique. The fast, direct, and quiescence, the size and shape of the powder material is immaterial. So this slide now shows data for 2 samples of a sintered alumina used as a catalyst support supplied by a major UK manufacturer. The material is milled to a constant modal particle size, measured, of course, on diluted samples using a laser diffraction device. However, it was known that there are differences in subsequent performance characteristics, and it was postulated that this was a consequence of the presence of fines in the dispersions that were not being detected by the particle sizing device. So one of the disadvantages of light scattering devices is that the presence of fines are obscured because of the scattering characteristics of the larger particles itself. Now, as seen on the right here, what we have basically is an NMR tube, and you have an RF coil around basically here in the instrument, and the NMR tube sits in that. So what happens is, as particles sediment passed through the RF coil measuring zone, they go past it. So you can actually measure very easily sedimentation by NMR relaxation. So what we do here is, now we've seen here, we've made the measurements, and you can actually do a single scan run in as little as 2 seconds. So this makes it really ideal for studying time-dependent effects such as sedimentation. Indeed, things even like crystallization and nucleation itself. Further, the important thing about NMR relaxation is that measurements are non-invasive and non-destructive. So samples can be stored for reanalysis, and this allows then study of accelerated aging or shelf storage. You can keep a sample, you can take it out, you can bring it back a month later, put it in the NMR and measure it. You haven't done anything to the sample itself. So what we show here on the data for these 2 samples of alumina prepared by milling it at 2 different processes, low shear and high shear, and we see the profiles are completely different. The initial T2 values are different, 68 milliseconds to 79 itself. But what happens in sedimentation, of course, over the first few minutes, it's all the big particles basically falling out. And now what you've got now, this here, is because of the smaller, basically colloidal sized particles in this case in the sample, and you can see there's a major difference. The rate, even the 2 rates are different. The rate of sedimentation, this one is about twice for the high shear. Now, I truncated the data initially at 6 hours, but I left the sample there and brought it back after 3 days, and after 3 days there's still a major difference between the relaxation times. itself. And this says that even this, there is a considerable fraction of fines remaining in the suspension. Now, the T2 relaxation time is a surrogate for the surface area to volume ratio. So these changes here would suggest that the particle size distribution is relatively narrower and more uniform in the high shear process than in the low shear process itself. So no matter what time scale is chosen over to which to monitor sedimentation or settling, the measurement of relaxation now can clearly differentiate certainly these alumina samples. And I've also done some other measurements on other materials like titanias and even things like copper phthalocyanide dyes and other pigments itself. So this is stability. What about aggregation? Controlled coagulation and flocculation are used to create specific structures in suspensions, such as paint, but also for removal of unwanted solids in, for example, wastewater treatments. Here I'm just going to show some simple examples of aggregation and de-aggregation. I prepared 4 aqueous suspensions of nominally 260 nanometer pigmentary grade titanium dioxide simply by mixing in water at pH 8. Uncoated titanium dioxide is hydrophilic and is readily wetted by water. And the zeta potential I measured, which is related to the surface charge and hence stability, was about minus 51 millivolts. This spot here. I just measured the sedimentation time. And you get it to sediment. Why? Because titanium has a density of 4, so even the small particles will settle. And there is settling. Why? Because just taking TiO2, mixing it with water pH 8, you're going to get a dispersion, but it's going to be a coarse suspension. It's not well dispersed because it still comprises aggregates and agglomerates. And we all know that you can get a much finer dispersion if you use a dispersion agent. So the first dispersion agent I used was adding some alum. Alum renders the surface charge of the TiO2 cationic, and I measured, in fact, plus 62 millivolts and measure. And what we see now is, because of this, you get deaggregation, a much finer dispersion, and the sedimentation rate is reduced by at least 50%. But you can do even better by choosing tetrasodium pyrophosphate, which basically makes the surface even more negative in this case. And in this case, you see that you've got a much finer dispersion. And in fact, the settling rate is not quite 0, but basically it's really very low itself. So, excuse me. In fact, over this, I measured it over about 2.5 hours. There's very little change. But what I then did is take this one, which is highly stable, and then just throw in some 0.145 molar sodium chloride, physiological saline. And what happens at this point, of course, you collapse the double layer, you get massive aggregation by coagulation. And of course, then you get a dramatic increase in sedimentation time. And basically, as I said, you can actually engineer this measurement about every 1 to 2 seconds. So you can get some very fast aggregation processes here. So I'm just showing this to show you can follow kinetic processes. Now, suspension stability is an arbitrary concept because it depends on the time scale of the experiment that you're taking out. And the question you have to ask yourself in a suspension is, do you need to have a suspension stable for 1 day, 1 week, 1 month, or 1 year? You have to prepare your samples for those conditions itself. And as I think I've tried to demonstrate, the magnometer can be used to monitor not just fast kinetic processes, such as coagulation, flocculation, but also then long-term processes such as accelerated aging. And I'll show some data a little later on one of those itself. So remember, we now got the basically stability and structure. Now we're going to come to structure. Rheology is the science of the deformation and flow of matter under the influence of an imposed mechanical force. Okay, it's a subject of tremendous technological importance. Not surprisingly, then, understanding and measure the characteristics are of economic interest. So here I want to simply show how NMR relaxation can be used as a tool to rapidly screen the rheological characteristics of emulsions. Now, there are 2 limited types of rheological behavior possible: deformation elasticity, and flow viscosity. Emulsions, however, are interesting. By the way, as well as emulsions, this also applies to semi-solid formulations. With mixtures of two immiscible liquids, they have mechanical behavior that's intermediate. They're, in fact, what's called viscoelastic. But there's a strong relationship between the structure of emulsions and their flow and deformation characteristics. And that's why sensory features of cosmetic products are one of the most important characteristics for consumer acceptance. For example, in the industry, it's called consistency. It's just basically viscosity. This plays an important role in the feel of a product. The consumer expects a higher consistency, for example, for a hand cream as compared to a body lotion. Now, a rheometer can measure both absolute values of both viscosity and elasticity under well-defined conditions. However, they do require a skilled operator, extensive training on hardware and software, and they take a lot of time. So the devices are not really well suited for quality control environments where rapid assessments are a key. Now, what I'm just showing here are 3 pairs of different cosmetic lotions. Each pair, Jergens, was compared with its generic equivalent, Aveeno with a generic equivalent, Gold Bond with a generic equivalent itself. Although the 3 brand name products are all lotions, they each have been formulated differently. They'll contain different ingredients, different composition, maybe even different processing, but they're marketed to customers providing distinctive tactile sensory attributes. The rheological characteristics, viscosity and yield stress, were measured for all 6 cosmetic lotions. I used, for anyone's interested, a TA rheometer model AR1000. You could use any one there. And I'm just showing you a representative plot for the first lot, the Jergens and the generic data here itself. Now, from this rheological data, we can obtain two parameters of the emulsion, the viscous and elastic. The first is the zero shear viscosity, and the second is the yield stress. So you can get this from the rheology data here. I've got the viscosity and yield stress. Now, emulsions, as I said, are 2-phase systems. There are 2 liquids. So there'll be 2 major intrinsic relaxations, a short time and a long time, characteristic for the total oil phase and for the total water phase, respectively. Now, by the total oil phase, I mean the oil phase with everything that's in it, not just the oil, and similarly for the water. And the table here summarizes the results of the relaxation and rheology measurements. The absolute values of viscosity and elasticity are, as expected, not the same for each brand products because they've been formulated differently. Jergens is not the same as Aveeno, is not the same as Gold Bond. But when we look at these generic pairs, these should be, if everything is copacetic and they are actually perfectly equivalent, they should be the same. But it is clear from the rheology they're not quite the same. And what we see clearly is both the short and long relaxations are not the same. But it is also, you can also see now that the NMR relaxation times are associated with viscoelastic characteristics. As the viscosity increases, the value for the long T2 relaxation time decreases, and as the yield stress increases, the short T2 time also decreases. Now, I'm not saying, I'm not even implying that NMR is going to be used to replace rheological categorization. Simply that what you can use the magnometer for is to rapidly screen cosmetic emulsions in order to prioritize the need for thorough quantitative viscoelastic analysis. And so the NMR relaxation in this case should be thought as a complementary tool to aid you before you go to the point of making all these exacting measurements. Let's move on now. Okay, so we're looking now into using the relaxation, now moving down the scale into R&D products. And I'm just going to show here it used in the development of a drug. Paliperidone palmitate is a blockbuster drug marketed actually in the US by Janssen Pharmaceuticals, and it's under the name Invega Sustainer. It's used to treat schizophrenia and schizoaffective disorders itself there. Now, a major US manufacturer of generic pharmaceuticals sent me 10 samples for NMR relaxation time measurements, together with a sample of the Invega product, what they wanted to do was to make a genetic equivalent because the paliperidone palmitate is coming off patent. So all I did, they sent me the samples already made up that they sent me, and all I did was put them directly into the NMR tube and measured them itself. And I just got the data. And what I plotted here is the relaxation of the batches they sent me as a function of relaxation time. And what I did is I simply assumed a 10% variation. I've just arbitrarily drawn a line 10% above the target, which is Invega sustainer, and 10 below. Now, this is because in any new drug application, certainly to the US FDA, is that in any metrics that you give them, they will allow an error of plus or minus 10%. So I just arbitrarily drawn this line here. And what we say, if I do that, you can clearly see that two of these batches are out of spec. It's very simple itself. Again, to do more than this, you'd have to do more method development, etc. But I simply showed that of these batches they sent me, if I draw this arbitrarily, two of these are out of spec itself there. Now, since the measurement I've said is non-invasive, what you could do is take these samples now and wait a period of time. Now, when you submit an NDA to the FDA, they have to be tested also in compliance with an applicable international committee on harmonization guideline, such as storage at 45 degrees Celsius for 3 months at a known relative humidity. So all I did is I took the NMR tubes, put them in an oven, basically at 45 degrees itself, and then pulled them out after 3 months and measured them again. And I took the samples, all the samples here that were in spec, put them in, and now over time at 45 degrees, these samples are aging. By aging, what's going to happen is you're going to get some particle aggregation, which means the relaxation time is going to go up. And what we find now is that we get a change of all of them. They've all changed because they've all been sitting there for a period of three months. Now, again, I've simply arbitrarily set a fail line now of 2,200. And what we find is two of those samples have gone outside of this. And according to this line, then those two samples will also not be acceptable. And of course, if you're going to do it in reality, this would need a lot more study and method development before actual implementation. But what it shows is the proof of concept that you can use NMR relaxation to do these studies for you. So let's go on to a different material, inkjet pigments itself. Two important physical properties of inkjet pigments are size and wetted surface area. The finer the particle size, the more intense will be the color. The greater the surface area, the greater will be the extent and uniformity of surface coatings itself. So in this study here, I took some aqueous dispersions of various inkjet pigments supplied by a major US manufacturer. They were yellow, magenta, and cyan, and the materials in question were considered as standards. For the yellows, 2 different primary particle size pigments were tested. For any suspension, the relaxation time decreases with increase in concentration. So what here, they're not quite the same because the solids they gave me. So I actually normalized all the data to take account of concentration. But each set comprised batches that had been subjected to the same processing, but were formulated simply with different polymeric dispersing age. Each pigment pair, A and B, C and D, etc., 2 different polymers were used, one for A and a different one for B. And then each suspension was tested for hiding power using a procedure adapted from the American Society for Testing Materials standard method for determining hiding power of paints. Basically, it's a draw down on the surface, and you can measure the intensity of the color on a standardized either white or black background. The data in the table summarize the surface area values calculated in the measurements. As might be expected, the data correlates well with pass-fail criteria for hiding power. It's also clear that relaxation measurements can discriminate not only between materials of different particle size, but also between the efficacies of different polymeric dispersant aids, as already been shown earlier in slides 7 and 8. And the speed and simplicity of NMR measurements with the Magnometer make it a really good tool for routine quality control purposes. itself. So the advantage of such measurements is that important characteristics of materials can be monitored quickly and easily at virtually any solids concentration, thereby saving time and money. So that's just basic R&D. What about actually processing itself in a real world? Now, zinc oxide, the microfine variety or grade of zinc oxide is different from the pharmaceutical grade and industrial grade in that the particle size is very much smaller. Typically, it's way less than 200 nanometers. Now, this size, visible light scattering is minimized, so the particles actually appear transparent on the skin. Everyone who's in the old days used zinc oxide knows you put it on and you look like kabuki. That's not acceptable anymore. You want to put it on, you don't want it to be seen. Well, all you've got to do is get the size down below 200 nanometers and the human eye can't see it. Okay. Now, these zinc oxides are now used in a wide variety of sunscreen products, particularly beach products, which are water in oil. Okay. Now, when you buy microfine zinc oxide, it's typically sold commercially at high solid suspensions in a variety of non-aqueous vehicles itself. And these are then incorporated in the oil phase of the specific water oil emulsion system. In actual practice, a batch premix is initially prepared, and this slurry is then transferred to a high shear milling device. But no matter which method is used, it's necessary to monitor the milling process over time, again, to avoid costly and wasteful overmilling. And the slide here shows data for two high solid suspensions of the same microfine grade of zinc oxide. In the first, seen as the red curve, the zinc oxide was initially dispersed at about 52 weight percent in a solvent called C12C15 alkyl benzenate. It's an emollient that's used in cosmetics, and we see what happens here. The surface area is about 50 square meters, and as you now mill it using a cavitation device at increasing pressures, you see it breaks it apart. The surface area goes up, levels off, and about 2,000 RPM over that, you're overmilling and you're getting aggregation itself. By the way, the measurements again were made at 52% solids with no sample prep. They were taken directly out of the mill and just put straight into the NMR tube itself there. So the next blue, when we in the blue one here, what we're doing now is adding a very small amount of a dispersing agent. The dispersing agent I used here was a polyhydroxy stearic acid, and shows you how really efficient this can be. At 0.5%, by just putting 0.5% in, first of all, at the very beginning, you can bump up the solids concentration to about 60% from 52%, and you get a much better basic dispersibility. Now, when you take that and push it through the cavitation device, it goes up again, goes up. But now you find that above about 1,000 or so PSI, you're overmilling. So what we've now got the idea that using a dispersant, we get better data, but we can now mill to a much lower pressure before we get overmilling. And this is the optimum here. Since milling is expensive, we're now saving time, effort, and money by monitoring basically the whole of the process using the magnometer. The interesting thing about the magnometer is that it has no moving parts. So in theory, you can actually make this online. You can actually take a sample straight out of a mill and pump it through the system. But I basically use this as a batch process itself there. So, but given the effect on performance features together with the economic implication of overmilling, using the magnometer basically provides economic advantages for a manufacturer in figuring out the most efficient, again, dispersant to use and the most efficient milling conditions under which to make the product itself. And I'm just going to show one more example of processing of cellulose nanomaterials. CSMs are naturally occurring nanoparticles in lignocellulosic biomass, and there's a lot of work going in because it is considered that they could, in principle, basically be used to replace even nanographite itself. The problem of CNMs is they are very, very heterogeneous materials, asymmetric particles, and analyze them is really, really difficult. There's a real need better to characterize before you can move forward from making these and getting them in a real process itself. Although the CNM has a potential to change the current paradigms of nanotech, if you can't measure these materials accurately and precisely, then you're not going to be able to go into a production in the production process itself. So what I just showed here is I've compared the relaxation times between a wet, in the original milling, wet, never dried samples, aqueous samples from initial processing, and then suspensions of the same CNC after drying and then redispersion. In the wet sample here, what we've got is called Na and MEPH3. What this is a cellulose nanoparticle that's been actually modified. The surface is basically modified with a salt to make it basically, this is basically sodium. And this is a methylphenyl phosphate, which makes the surface basically, excuse me, itself there, which makes the surface actually more hydrophobic. And now we know this because we've got data on inverse gas chromatography, because what it shows is when you put this methyl ligand, it results in a decrease in the dispersive components of surface energy, and in other words, making it hydrophobic. Now, why would you make it hydrophobic? Because these CNCs are used both in aqueous systems, but a lot of CNCs basically want to be dispersed in polymer melts. And so you need to have surface modification to allow it to be put into the melt. But what we see here in these wet dispersions to begin with, this is very well dispersed and this is poorly dispersed. Understandable, of course, because this basically is a more hydrophobic surface. But if you now take these CNCs and dry them and then attempt to redisperse them, what you find is the sodium one doesn't redisperse very well, because by drying it, what you now do is you've essentially coagulated the CNC itself there, and it's stuck together. Whereas although this one was not well dispersed to begin with, when you dry it, it redisperses reasonably well, because the coating on this material is providing some degree of steric repulsion and therefore limiting aggregation itself. So the major advantage again of the magnometer, because it's no moving part, in theory you could actually do this whole process in one step. You could push it through, you could dry it, you could take it out and push it back into the instrument itself. But this just shows again that you can take materials at any stage of process, in any form, put them in and look at differences between materials to see what exactly has happened. So let's now finally look at a real world finished product. One of the advantages of NMR is that you can put anything in an NMR tube. If you can get it in, you can make a measurement. The commercial products, such as, for example, commercial lotions, are very, very complex systems itself. Often they can actually contain 15 to 20 components there. But for an emulsion of known composition prepared by a fixed process, the average relaxation time should, with an experimental error, be the same. So if you put the same thing together in the same way, you should get the same relaxation, of course, with an experiment. And that's something you can do. But when you design commercial emulsions, as I said, it's very complex. It's not just an oil and water. The oil phase can contain surfactants, emollients, humectants, thickeners, and the water phase can contain the same. Now you can mix them in the water phase and oil phase beforehand, and then you affect the emulsification process. But during that emulsification process, you also get partitioning then of the different components, and you can get partitioning from one phase into the other. And what you get at the end is the end result of the lotion that you've made. And the NMR relaxation value you get is that specific fingerprint for that particular emulsion itself. Being multi-component, it means you really can't dilute these materials without consequence, because The dilution process destroys any structural characteristics and can also induce stability, leading, for example, to creaming and often breaking itself. As I said, the magnometer's measurement technique is non-invasive, non-destructive, and it can work with any type of emulsion, water, oil, or water, oil in water. So when we put it together, what we do is we're putting in there and we're getting the end result. And because it's two-phase, we get, again, a short T2 and a long T2. The short T2 is what you get because of the oil phase, and the long T2 is what you get from the water phase after emulsification itself. Now, brand recognition and brand awareness and brand loyalty are different concepts, but they are equally important in the marketing. And this is very true for cosmetics. So I'm just showing the same samples. These are the samples that I actually used to do the rheology on the earlier slide, the Jergens, Aveeno, and Gold Bond here. So, and if you go, for example, and take this value of this generic from Walgreens. I think Walgreens in the UK is called Boots, the chemist. You read a little, says here, it says compare to Aveeno brand name product, and it tells you to compare it to this one. So what I did is I actually went to the store and bought these pairs which were comparing itself there. From the oil, from relaxation, you will get the percentage of oil phase and percentage of water phase present in each of these components, because it's based upon the amount, the short T2 and long T2. So we see when we do this, the oil phase is 21% oil and 78% water. The generic component, okay, although it on the back of the product seems to contain all the same ingredients, finds it's 30% and 7%. They're not really the same, and we got the same results for each of these generic pairs itself. So it suggests that each emulsion is different. And what does this mean is even if you're using apparently the same products, the partitioning into the oil and water phase is clearly different. So this means it's likely that some of the raw ingredients themselves must differ. So measurements using the magnometer allow a formulator to answer the question, would two products that purportedly contain the same ingredients perform the same? And we can see here the answer is not necessarily so. So we can now use the magnometer, for quality assurance purposes in actual real products. And one again is that although there's oil here, this is a micrograph literally of the studio one, and I defy anyone on this one here to even work out where the oil droplets are. So you can't do easy analysis, but NMR can give you at least a fingerprint of what you've got. And the other point, what it means is that you can now use this to compare and contrast competitive products as a means to improve equivalency or the economic of formulations. So this is a material that you can get into an NMR tube. But what about a material that you can't get into an NMR tube? Well, one of them would be actually a piece of automobile tire. In the tire industry, carbon blacks added to rubber to enhance the compound physical properties itself. Carbon black is non-spherical, and determination of surface area from size and distribution is difficult, since dispersions are inevitably comprised of aggregates and conglomerates. But the surface activity of carbon black has a great influence on the reinforcing properties in tire making. In the industry, they call it surface activity. It's recognized that it's related somehow to the surface chemical properties. And carbon blacks are typically prepared from different processes, one of which is oil furnace and one is gas furnace processes itself. But what it means is that the carbon blacks that come out of there at the end of the day when they're made contain significant amounts of heteroatoms on the surface. And these heteroatoms basically are oxygen, sulfur, and nitrogen. Oxygen is acidic, sulfur and nitrogen are basic. So that when you've got these materials, the ratio of those materials and how you treat it means that the carbon black itself chemically can be different. NMR relaxation, as I said, is sensitive to the extensive wetted surface and suspension, but it's also sensitive to the chemical nature. itself. Indeed, it's unique in this respect because most traditional instruments are sensitive only one feature, particle size or zeta potential. So NMR is sort of mitigated. You get a balance between the surface morphology and the surface chemistry. Of course, it's not possible to put a piece of tire in the magnometer, and neither, of course, is it possible to measure carbon black dispersed at the high temperature in the polymer melts they use to make the tires. Nevertheless, relative differences in the available wetted surface area of carbon blacks dispersed in a solvent should trend with the state of dispersion of the same blacks in a polymer melt. The difference is the difference from a colloidal percentage, what's called a difference in the Hammaker constant itself there. So you should get the same trend itself. So if you shows you get better dispersibility, then relaxation should show you the same trend in the solvent itself. And to test this hypothesis, I obtained 4 samples of carbon black for a major tire manufacturer, 2 oil furnace blacks and 2 gas furnace. The relaxation times were 10% in a mixed solvent system, and I measured them directly on the tire. I measured them directly on the sample, and then I compared the measurements from surface area compared with the actual measurements of tensile strength, relative abrasion, and road wear on the tires themselves. And we see now there's a strong correlation with the 3 important end-use performance testing data measured directly on the tires. So again, the Magnometer measurements can be used as a rapid screening test in order to prioritize the need for further thorough quantitative testing. But also, importantly, if something goes wrong, you don't go through the whole process of making the tire and finding you can't do anything about it at the end itself. So at this point, I've shown a series of examples that I hope have demonstrated the wide utility of NMR relaxation measurements to investigate general issues of particle calibration in various aspects of formulation. And I'm coming to the end, but I just want to try 2 more specialized examples. The first one is the comparison of wetted surface area from NMR and comparing it with dynamic light scattering, static light scattering for a drug. Now, the surface area of an active pharmaceutical ingredient directly impacts its performance, its bioavailability, and its cytotoxicity. You want it to be highly bioavailable, but the problem is you also don't want it to be cytotoxic. So the less you can use of the drug, the better off you are. Now, the rate of dissolution of an API is driven by both concentration and surface area as dictated by what's called the Noyes-Whitney equation itself. You reduce the size, of course, by milling, or you can bake it by bottom up by nucleation itself. But no matter what, the API, the particles are invariably not spherical, as been seen in this photomicrograph of one of the drugs here that I'm working with. So I'm showing an example for 2 drugs here. One is an appetite enhancer. This is actually was one of the first so-called nanoparticulate suspensions produced. It is now sold as an appetite enhancer for people who have AIDS. It's basically made by nucleation process, and I just took the sample as was made, put it in the NMR, measured the NMR relaxation, and then I also took the sample and diluted it and measured it using dynamic light scattering. And we see here that it's a pretty uniform distribution, quite reproducible, with a mean size of something about 240 nanometers. Now, if we assume a sphere, we can actually calculate the surface area. It comes to about 18 square meters, but I measured 38 square meters. Why am I getting it? Well, surface area trends with simplistically with d squared, which means NMR measurements are very sensitive to the finer end of a distribution. So interestingly, if I go to the d10 of this distribution here and take this value here at the d10 size itself, and then calculate the surface area, I got 38 square meters, which means what we're getting here is you're getting a value from NMR, which is telling you more about what the actual total surface area is, not basically what the mean value would get from a size calculated assuming a sphere. This one over here was an antiretroviral drug. It's dapivirine, used basically, it's a non-nucleoside reverse transcriptase inhibitor used in preventing HIV from replicating it's used basically to combat HIV itself. The material was supplied as a dry powder, it's made initially at about 300 microns, and then it is seriously jet milled down to sizes to get it all the size down to less than 10 microns. You take a 10 weight percent of the material, because it's going to be placed in there, measure it itself. And what it did is I then measured the surface area. Now, this also points to the fact that sometimes you need to do a couple of measurements, because the mean size of this was 2.4 microns. But note, if you measure you see it's a bimodal distribution. If I take the mean value, which is about 2, I get a surface area of 2 square meters, but I measured about 24 square meters itself. Excuse me. However, again, as I said, this is bimodal. If you now look at this little peak down here, where this one is, and you take this size here, the D10, if we can do if you look at the cumulative distribution at about 10% here, you see at that point there, you now take the D10 and take that value and calculate it. It gives you about 24 square meters per gram. In other words, 10% of this API is providing 90% of the total effective surface area. Clearly, the importance of knowing the surface area because of bioavailability and cytotech. This is important. But if you'd only measured a mean size, or not the distribution, or you'd only measured MR, you wouldn't know that what was going on. You get two numbers, and in this case, you'd say that either one of these two numbers is wrong. What we're saying is that the NMR is giving you complementary information that dynamic and static light scattering can't give you itself. Finally, I'm just going to talk about microemulsions itself. Microemulsions are very interesting systems. They're completely different from regular emulsions. They are isotropic mixtures of oil, water, and surfactant, and usually with a co-surfactants. But in contrast to ordinary emulsions, which are thermodynamically unstable and phase separate, microemulsions are thermodynamically stable and don't require high inputs of energy or shear conditions. They almost form spontaneously, but they only exist at very specific concentrations of the various components. They cannot be diluted itself. But you can put a microemulsion into an NMR tube. The other thing is that microemulsions do tend to be totally clear, so you can hardly do light scattering on these systems itself. So characterization of a microemulsion is pretty problematic. You can, of course, use pretty complicated systems such as X-ray and neutron scattering, but again, these are not really well suited to standard laboratory analysis. Now, I've just shown two graphs here of two systems where I made a model system, and what I did is I actually added some dye so you could actually see the difference. So you make it up, and what you've got is an oil-rich phase, a microemulsion, and a water-rich phase here. And what I've just shown, this one piece of data, is the Shore T2 tracks directly with the percentage of oil in the phase. So you can play around with the type of oil, type of surfactant, and you can actually, by measuring the T2, basically figure out what's going on with the oil phase. But that's easy. But more importantly, let's look at the water phase. When you start off with making any emulsion at all, never mind a microemulsion, you're going to take a water phase, and that water phase is going to contain probably some surfactant or something else. So you can actually take the water phase, ready to use it, this one here, measure it, okay? And then you can measure it after basically the emulsification. And what do we actually see here? Okay, what we see is that we're starting with this initial phase, number 6. This is the value here of the water containing the surfactant. This is just sodium chloride. So adding the surfactants changes the relaxation time because of the presence of the tenside that's in there. When you emulsify it, it goes up. When the relaxation time goes up, what it's meaning is the surfactant is going out of the water phase into the microemulsion. So one of the things this is saying is you can track basically the partitioning of the different surfactants into the different phases when you're making microemulsions. So what it's saying is that you can actually routinely fingerprint microemulsions, not only the initial composition of the oil and water, but also the subsequent system itself. So I've tried to cover a real amount of material today. I have basically application notes and things on all of these. If anyone's interested, contact Keith and I'm more than happy to send you little notes on all of them itself there. But I've tried to cover a comprehensive range of general applications where NMR relaxation can be, I think, of real use to formulators. So in conclusion, I hope I've been able to persuade you that NMR relaxation measurements can be used in almost any industries and applications, but it gives you significant potential to provide insights into complex formulations. It's an informative technique that complements other traditional techniques, but often can provide information and intelligence not possible with those. And so I believe NMR relaxation should be considered as a primary particle characterization and surface analysis technique. And you can use this, the magnometer, from blue sky exploratory research and development through quality control to process monitoring and product testing, literally, as I said, from fundamentals to end use. As such, I believe that it can help facilitate the drive of formulation from an art to a science. Thank you very much for your time. And I think we've run over a bit, but if Keith, we can probably take a few questions if people are interested. Thank you so much.